We understood about what is the force that exists between any two current carrying conductors. Now, let's try to understand, supposing you have a dipole that is aligned in a direction not exactly along the direction of the magnetic field. Then what is going to happen? The dipole will tend to align itself along the direction of the magnetic field or perpendicular to it, right? As a result, there is going to be a torque that is going to be acting. In a similar way, there is also going to be a torque that is going to be acting in a current carrying loop. Let's try to understand about these definitions and these examples of torque in this particular topic. We have understood as to when exactly is the force that acts on two parallel current carrying wires. Now, supposing we have a current carrying wire and we want to rotate it. So, if you want to rotate it, what exactly is the amount of force that is going to be exerted on it? As a result, that is what we are trying to find out here in the torque on a current carrying loop. So, if you want to understand what exactly is the torque that is acting in a current carrying loop. So, here if you see, there is a magnetic field, and in this magnetic field that makes this particular current carrying loop move. So, you have a force that is acting here that will tend to move along this direction, and similarly you have an oppositely directed force. So, at every instant of time, this loop will tend to move. This will tend to move such that it is making a direction parallel or anti-parallel or perpendicular to the direction of the magnetic field. So, how do we find that? Let's try to understand it here. If I say dF, so due to a particular current carrying element, so IDL cross B, this is going to be the net value of the free force that we have. Here IDL and B are perpendicular to each other, and therefore the force is mutually perpendicular to both the current element as well as the magnetic field. So here if at any instant of time, like we saw it here, if at any instant of time, let's say the current is making an angle theta, if the current is making an angle theta with the horizontal, let's say, so if this is this and I is the current element that we have, therefore at this point, like we saw it here, there is going to be a force ILB, and similarly same amount of force is going to be exerted towards the left hand side. As a result, what will we get? The net force is going to be given by FILB towards right and FILB towards left. So the torque that is perpendicular to it, depending upon how much is the length perpendicular to the force. So we'll take the sin theta component. So L sin theta into F gives us I L square B into sin theta, where L is the length between the two sides. If I have to write it, so I can also mention it something like mu cross B, where mu is nothing but I into A. So this is what is dependent upon, so this is what is known as the dipole moment for the case of a magnetic dipole. And A is nothing but the area, so L square is the length, I am taking a square loop, L square is the area into the area vector, that is the normal to area, we will put the area vector, unit vector in. So this is the area vector, so I times A, I is the current, so current is a pseudo vector, it is not a vector actually, that results into mu being a vector which depends on the area of the loop. So this is what tells us about the torque that is acting on a current carrying loop. Now if you want to find out how much is the energy of a magnetic moment, the torque tau is equals to mu cross B. This tries to rotate mu in a direction that is parallel to B. This is the magnetic moment that we have. Okay, now how do we find it? To rotate it, obviously you are applying a torque. When a torque is applied, how much is the work that is being done? The amount of work that is going to be done is going to be given by the work done dW. So dW is equals to tau into d theta. So that means to rotate the plane by angle d theta, you have to do the work that is dW. So that is how it is given. So if d theta is in the direction shown, then dW is going to be negative, and the potential energy by convention is going to be equals to minus dW. Why? Because when a work is being done, it is going to be kind of, you are taking something out of the external system and you are storing it. So obviously the energy of the system is going to increase, so we take that as positive, and the energy of the surrounding is going to decrease, so we take that as negative. So that's the reason we have a negative sign over here. Since tau we found that it's equals to nothing but the magnetic moment mu into B sin theta, which is a function of theta that we have. Therefore, what will we get? We need to just integrate this. So this tells us, for making it move by an angle d theta, you are putting in and energy, the energy that is utilized is mu b sine theta. So if you integrate it, so over the total all possible values of the angles, so you will get minus mu mb cos theta. Or if you just use the dot product, because this is nothing but the it's a scalar quantity, so that's the reason you will get minus mu dot b. Moving on further, if you want to explain this, so this is one loop, this is your another loop, the magnetic field between these two, so this is something that is missing. This is the north pole, you have the south pole, and this is the force that tries to take it perpendicular to it, and similarly this is the force that tries to bring it, means it wants to align it perpendicular to the direction of magnetic field. That's the torque that we have. As a result, what we are going to understand, so if I say let B is the magnetic field that is acting between the two poles that are given, N are the number of turns of the coil, that is more are the number of turns, more effectively is going to be the force that is going to be acting. And if I assume not a square loop, let's assume now a generic thing, let's say A and B are the two sides. So capital A being the area of the loop, and if I assume that I is the amount of current that is flowing. So what will we get? What are the sides which are going to be experiencing forces? You are going to be PQ and RS, not this one, and similarly not this one, right? Because this is along or anti-parallel to the direction of magnetic field. So there is no force being exerted, because for force to be exerted, it has to be perpendicular to the direction of magnetic field. So only the two directions that are perpendicular are PQ and RS. As a result, if we want to find out how much is the net value of force, so this is going to be IA cross B, which is equals to this. A is the side, and similarly for RS it's going to be this. So these two forces are going to be equal and opposite to each other. Therefore, what you are going to get, you are just going to multiply. The net force is going to be equals to this multiplied by the other side, that is equals to B. So as a result, the net torque is going to be just equals to IAB cos theta. So if you just understand this, so this is nothing but IAB cos theta. So B stands for the magnetic field, A is the area, I is the current that is flowing, theta is the angle that the torque that the loop is making with respect to the magnetic field. How much is the angle the loop is making with respect to the magnetic field? That is equals to theta. So if there are n number of turns, you are just going to be multiplying it by a factor of n. So this is the net result that you have, that is tau equals to NIAB cos theta. Going further, if you want to understand what are the different cases that we have. First case, if theta is 0, that is plane of the coil is parallel to the direction of the magnetic field. So you are going to have a maximum value of torque, which is going to be NIAB. Sorry, the I jumping around. Similarly, if theta is 90 degree, the plane of the coil is perpendicular to the direction of the magnetic field, and therefore the torque is going to be 0. If we are trying to find out normal to the plane of the coil, so if you are trying to find out normal to the plane of the coil, which is making an angle alpha, so obviously what you will get as a result, you will have something like alpha plus theta. Theta is the original angle, alpha is the other angle, and therefore they are going to be making an angle this. So you can simply write this as torque can also be written as NIAB sin alpha. So let me explain what I mean to say by this. Here this is with respect to the horizontal, and the normal to this is making an angle normal, such that this is equals to 90 degree. Now if you want to find out the net torque with respect to this particular normal, because it's going to be moving with respect to the normal, so the torque is going to be given by NIAB sin alpha. So this thing, if you want to write down, because why have we done it deliberately? Because we want to write down in terms of the cross product. So we have the magnetic moment vector, that is NIA, and we have the magnetic field, that is B. So M cross B gives us the net value of the torque that we have. So if you want to picturize this, so for instance here you can see that we have a couple of cases here. The first one, this is the direction of the current. If you are taking from the top view, this makes it, when the angle is 90 degree, effectively you have it something like this. Going further, if we take it for the case of 60 degree, actually it is 60 degree, then it's actually inclined. In a similar way, if you take it for the case of minus 30 degree, it's going to be inclined like this. For 0 degree, it's inclined like this. And finally, previously it was 30 degree, this is minus 30 degree. So this results into the net values of the torque. Hopefully you would have enjoyed listening to whatever we have discussed in the module. Now, if you still feel that there are any particular doubts that you have, so please visit our site www.askIITians.com. In this, go to the discussion board. Here you can find all the topics relevant to your questions. You can post your doubts in these relevant topics. And how exactly you are going to do it? Go to the right hand side corner of your screen. As you can see, you can select the category. The categories are defined here. You can select your category, type down your question. You can use your mathematical symbols as well. Else, if you have the question in the form of an image, you can attach the image, post it. We can assure you that the questions would be moderated and answered between 24 to 48 hours after you post it. So keep posting and happy posting. Thank you. So we understood about what exactly is the example or what exactly is the expression of the torque. What exactly is the torque? Torque, we know, is the force in which is required to rotate any object or a dipole towards or perpendicular to the magnetic field. And therefore, we also learned about if you have a current carrying loop, in that case, what exactly is the expression of the torque. We also understood about what exactly is the amount of potential energy that is required for this particular purpose. So stay tuned for more on this.